Every day, I give you insights into the analysis, characterization, and understanding of ultrasonic and piezoelectric devices. So today we're going to continue, and we're really diving kind of deep in these videos. We're going to continue on the non-symmetric resonance impedance. This is just recognizing if your behavior is normal, or symmetric, or whatever you want to call normal. It'll allow you to utilize student tools for analysis. I'm going to get into the actually next episode what the significance is, because I perhaps haven't really hit on the core of why you even care about these videos. Maybe I should have done that first, but hopefully these videos are interesting and important nonetheless. But we're going to go over the third reason today why the impedance response may not be symmetric. And the third reason is due to non-linearity. So non-linearity is a kind of a loaded term, because everything we do in college and high school, going back to those physics, if you did some type of frequency analysis or work to whatever extent, anything you do is always linear. There's always a linear relationship between stress and strain, between current and voltage at whatever frequency. So if you scale voltage, you'll scale current the same amount. If you scale applied stress, your strain will increase the same amount. That's linearity. So essentially linearity, if we define it, is the relationship where increasing a certain value, the input, such as voltage, will result in a constant, there's a constant related to that increase in current. So increase by X amount. So if you increase voltage by X, you'll get current increased by X as well, by a constant. And the really important thing about linearity I want to discuss is frequency in equals frequency out. That's another, perhaps another very important implication of linearity. Your frequency in, you put in 100 kilohertz, you're going to get out that frequency and only that one. If you get anything different, you will have nonlinear properties. So that's the first actually aspect of nonlinearity. Or the second one on my list, but it's the first one I just decided to hit up today. So you put in one frequency and you get on another. That's nonlinearity. The other part of nonlinearity is also a change in apparent linear properties. So you have a piezoelectric charge coefficient, or you have a compliance, which is the inverse of stiffness. So you have that value, but under certain conditions, that value changes. That value is no more. So the stress, so if you assume a function, right, the compliance S is a function of stress and equals strain, but it's also dependent on the stress itself, because, right, the compliance multiplied by stress equals the strain. So there's an interaction, there's a more complex, maybe we can call it nonlinear effect going on. So the linear properties actually become variable. So, and what that really tells us, and the really important point for ultrasonics and piezoelectric device analysis, is the conditions under which you measure your properties will determine the answers you get. So let's just keep that in mind. So let's take a look at the implication of this. Let's focus on compliance. So compliance, which is the inverse of stiffness, and using piezo speak, we talk about compliance, which is denoted as S. So assuming the very standard, kind of example where we're sweeping our frequency and we are approaching a resonance. So our amplitude of oscillation is increasing, and as is our current, due to the mechanical oscillation of our transducer. Let's take a look here. So let's do that. So as we increase in frequency, what's happening is that the compliance is increasing. So a higher compliance actually results in a lower resonant frequency. So as you kind of get close to the resonance, you are going to go faster and faster down that hill, because the resonant frequency is going backward. It's going toward you. And at a certain point, two things happen. At a certain point, you will be standing on the resonance frequency, and then you'll keep continuing going forward. So once you cross over the resonant frequency, we know that the oscillation level goes down. And if the oscillation level goes down, then the compliance is coming back up. So that this also have what ends up happening is that there's a sharp turn. There's a sharp turn to get into the resonant frequency, but as you're leaving, it sort of tails along with you. So, for example, at the frequency over here, where you're starting to get away from the resonance, the actual resonance, according to that the instantaneous compliance is now different depending on your oscillation level. So it results in a sharp turn going in and a slow transition coming back out. It also happens at higher voltages. You'll get discontinuities happening. So this becomes really challenging to analyze and pursue. So it's important to recognize this, why it's happening. It's not because necessarily you're doing their measurements wrong. The way to correct for this is actually to have a method of current limitation. And intrinsically, actually, impedance analyzers do have an finite output impedance. So you may have set your impedance value to 1 volt or half a volt, your voltage level to 1 volt or half a volt to drive your piezo, but that's not promising the voltage that is actually being delivered. The voltage which is actually being delivered is that 1 volt, and then you have your output impedance, let's say it's 50 ohms. And then you're measuring a 50 ohm load, so that half of the voltage gets dropped over your internal resistance, your internal your output impedance of your impedance analyzer. So what this means for piezos is that as we get to the resonant frequency and the current wants to skyrocket, it's actually going to be controlled to an extent. It's not going to be allowed to follow that trajectory of impedance as closely. So if you almost have a constant current, or more importantly, a constant power, or actually even more importantly, a constant amplitude, the maximum amplitude will be limited. So you won't have such a stark curve and coming back up slowly. That is actually very much true for when you're using a bench test and when you have an amplifier. And the amplifier, let's say, even has very low output impedance, and your device has a high impedance, but you're still driving significant voltage, drive significant power to produce nonlinearity. Actually, one of the ways to get away from nonlinearity, and the reason why impedance analyzers are sort of looked at as a standard of why we use low voltage to characterize transducers, is because at a certain low amplitude, we do assume that there is no effect of nonlinearity. These are the base level low excitations, but that's not 100% true. There will be always some aspect of nonlinearity existing. So what to do in this case? So you can either have a setting on your impedance analyzer. Most don't, but some have a constant current output. Some have the ability to change your output impedance, so you might want to change that as low as possible. The other thing is always note the conditions of testing so you can reproduce it. Even if there are nonlinearities, things that aren't ideal about your system, you can still reproduce it to make judgments about comparison of devices and also quality control. The other thing you can do is you intentionally put a resistor in series of your transducer, and you can calibrate the effect of that resistor out, but effectively that resistor is going to prove to increase the output impedance of your, apparently increase the output impedance of your impedance analyzer, and therefore the voltage over your transducer will drop at resonance because it's dropping impedance relative to that resistor, or the effective output impedance, the sum of the two, the air analyzer and your resistor. The other thing that happens, the second point that occurs with nonlinearity, is introduction of additional harmonics. So not only are your material properties excitation level dependent, that linear part, there's also nonlinear additions, especially with a third harmonic. What this typically appears as happens in this case is your values. So you have from your sine wave, you actually get triangle wave type behavior. That's a clear sign that you have the third harmonics existing in your system. So in order to do appropriate analysis in this case, you'll have to do an FFT to extract the first and third harmonics. You can actually still do impedance analysis by using your first and your third harmonic ratio. So that means your input voltage, which was assuming we're going to assume that it's the sine wave, so you have one very dominant harmonic, and your output is 2. So you almost have 2 impedances. So your impedance of your third harmonic and your impedance of your first harmonic, and both of those can be analyzed and used for analysis. Mainly, for impedance, you'll use your first harmonic for that level of analysis. In that case, it's also important to note your average power that your transducer is dissipating. This is more toward the bench test. This is not really going to happen when you're driving with the low voltages appearing in your impedance analyzer. So in the next video, so this ends this video. In the next episode, I'll be talking and I'll be kind of setting the stage again. So why do we care about non-symmetric impedance? And I will describe some, again, recap those methods that we can use to still analyze our transducer despite the apparent mismatch of experiment and the theories and the rules that we typically use to apply. So please see the description if you want to be subscribed to getting these videos, getting an update when they're released in your email. There'll also be a transcript that you can skim more quickly to see if the content, it's worth your while investing. I think all these videos are super important for somebody working with ultrasonic transducers. Imagine missing a problem like this, like that curve, and having variability in your analysis and become very, the lack of ability to properly apply the correct theories in order to produce the correct design decisions. So thank you for watching this video, and I look forward to seeing you on the next episode of The Shock Show.